lecture. So we will now start with the module 1. Do you see the screen?
Yes, sir.
Okay. So module 1 is now introduction to structural steel design. So our intended learning outcomes at the end of the lecture, the students will be able to first define structural design, second, enumerate and explain each step of the iterative design procedure for structures, identify and differentiate loads acting on structures, enumerate and differentiate design philosophies used in structural steel design, define structural steel and what its contents are, describe the processes involved in modern structural steel production, classify structural steel according to its material content and cross-sectional shapes, and describe the general material behavior of structural steel. So module topics. So topics in this module include the structural design process, minimum design loads for structures, philosophies and structural steel design, composition and manufacturing of structural steel sections, and material behavior of structural steel. Right, so for this meeting, so we will still have a meeting this Friday. No? Although for the next weeks, starting next week, we will not be having meetings on Fridays. No? Ngayong week lang since we had our orientation last Monday. Okay? And as far as the poll results are concerned, the results of the survey yesterday, majority of you actually, all of you preferred twice a week meetings. Okay, so we will be doing twice a week meetings. So in this section, Monday and Wednesday, 7:30 to 10:30. Okay. Let me start. So this module is divided into two parts. The part one is the structural design process, design philosophies, and relevant code provisions. So I will only be discussing part one for today. So, okay, so nowadays building construction can be seen at just about any urban area. So buildings are these are done in pace with the rapid development of these cities. So in order to support the development of each city, construction must be supported. Construction must be done since we need more because we need more infrastructure to support the functions of the cities. So for example, if you want more people to live in a city, you need to build more houses, more say apartments, more condominiums, etc. Uh, so to increase the if you want to increase the literacy of a city, the educational literacy, you need to build more schools, etc. So now, as we observe, buildings or any other structure in question are made of some of the materials that we are already familiar with. Some are made of masonry, so CHB, hollow blocks. No? So that's one example of masonry. Concrete, so either the most commonly used concrete for building construction is reinforced concrete. Concrete with reinforcing steel. No? Or you may also use pre-stressed concrete, especially for bridges and flyovers, or structural steel. So these are the common materials that we use, especially in the Philippines. So in this course, we will be mainly discussing design of structures using structural steel. So structural steel is usually used in almost all types of structures that we have. So this is an example of a steel building. So I'm not really sure where is this. No? So but if you want a local example, that would be the one. If you observe, no? If you usually go to Anonas, beside the WCC hospital, there's a parking building ongoing construction there. So that's an example of a steel building. Okay? So these are the beams, the girders, columns, the bracings. So those. Here is an example of a steel bridge. So this one is the Quezon Bridge in city of Manila. So here are the members, and then we also have the connections here. We call them rivets. No? Although the use of rivets is now obsolete, we use now either bolts or welds. No? So there you go. So based on the AISC, again, AISC stands for the American Institute of Steel Construction. So you may click this link. No? So I just adapted this one from there. So what are the 10 reasons to use structural steel? So what would be the advantages of structural steel compared to other building materials that we use? So first, cost effective. Compared to other framing materials, structural steel brings greater value to a project in terms of initial cost as well as reduces cost in other areas such as foundations, general conditions, and facade systems. Because in concrete, for example, if you want to design a facade, you need a more intricate detail. No? Also in foundations, you need more intricate detail. No? In structural steel, it's not much of a problem. Detailing is a bit easier. No? Second, accelerated schedules. So structural steel is fabricated off-site while preliminary site preparation and foundation work are being performed. So if you observe, in reinforced concrete construction, you first lay out the formworks and then you install the reinforcements. And that's the time that you will now be allowed to pour the concrete. And the pouring of concrete, and the quality of concrete during and after pouring depends on several factors like temperature, humidity, the distance from the batching plant to the project site, and all. No? So the quality of concrete may vary. However, in steel, that would not be much of a problem. Although you still use a concrete, especially for slabs. But for members, you mainly use steel sections. No? So in this case, you just need to install them, and the installation is much faster than concrete pouring for beams and columns. No? There's and at the same time, it is also cost effective. So I'll go back to number one because you don't need for works in this case. The next, increase usable floor space. So So structural steel is both light and strong, allowing for long spans and all open column-free spaces. So since we know that structural steel is a lot stronger than concrete, well, that's the reason why we use them as reinforcement. No? So and at the same time, they can be light precisely because the sections for structural steel, especially in terms of cross-sectional area, are much less than that of concrete because as we know, the strength of a structural member depends on both its section and material properties. So if the material is weak, then you need to compensate it by providing larger sections. And larger sections will lead to larger volumes, which would lead to larger masses. Okay, that's why if you want a lighter but stronger structure, you can use structural steel. And at the same time, you can use structural steel for longer beam spans. Because it is stronger, then deflections will be less than that of concrete. That's why uh, you can use steel for longer spans. Unlike for concrete, usually you cannot go beyond 10 meters. Espe- Uh, based on my experience, you can use reinforced concrete for up to around 8 to 10 meters. Beyond that, it would be pre-stress. And pre-stressing is a lot of work. That's why uh, that's why we use structural steel. Okay. Next, aesthetically pleasing. So structural steel frames provide designers with a wide range of options for addressing a project's aesthetic requirements. Structural steel can be rolled, curved, and integrated into irregular building shapes. At the same time, its small footprint contributes to a sense of transparency for the building. So structural steel can be formed in many ways. Uh, you can also use structural steel for facade. So, although in concrete, it offers more flexibility in terms of shape. Apparently, concrete is much harder to be used for decorative purposes because you need to check out the quality of the concrete. No? So, as I have said earlier, if you pour concrete, the quality may vary depending on the several factors. Next, future adaptability. An existing steel frame can be easily modified to address changing building requirements and uses. So, for example, you want an extension, it will be a bit easier for you to design the extension of a building using steel from a steel building, from an existing steel building. In concrete, although you can design for the building extensions, for example, there is there's a there will be a problem, especially if the existing members are inadequate. Another example for this one is for retrofitting. Retrofitting of steel structures is a bit easier and less complicated compared with concrete. In concrete, there are a lot more methods to do retrofitting. So why do we do retrofitting in the first place? Because of the changing code requirements. So for example, you have an old building. Since we are sure that they are designed using old codes and specifications, you may be it is almost sure that it will not fulfill the requirements for the updated codes. That's why you need to retrofit them. No? So in steel, retrofitting is a bit easier compared to concrete. Excuse me. Next, quality and predictability. Structural steel is fabricated off-site under controlled conditions, ensuring a high-quality product and reducing the number of costly fixes at the job site. This also allows for just-in-time delivery, which accelerates the overall project schedule. So, all concrete may also be fabricated offsite. We call them precast concrete. However, it is limited. So, it is only limited to, say, slabs, walls, non-load bearing walls, and intermediate beams, for example. For framing systems, precast concrete is not recommended. So, unlike that, structural steel can be fabricated offsite. So, for example, you need a beam of this length, they can give you that length. If you want the connections to be in this detail, they can give you this detail offsite. So it allows more control on the quality of the materials that you use. Next, ease of design. Structural steel is produced to precise tolerances and consistent strength levels, which, when combined with an established, well-documented design approach, can greatly simplify the design process. So, as I have said earlier, structural steel is more consistent in terms of its properties, no? Rather than concrete. In concrete, you need to test the concrete that you pour every now and then. And again, the uh, the properties of concrete may vary depending on the actual site conditions. That's why concrete is a lot harder to uh, to quality control than structural steel. Next, enhance productivity. Structural steel leads the construction industry with a fully integrated supply chain that uses advanced technologies like computer-aided manufacturing and BIM at all stages of design and construction. These technologies have been proven to reduce or eliminate errors, improve safety, and lower project costs. Pretty much related to the earlier reasons. Uh, Next, green. So structural steel is green. So today's modern steel mills produce steel containing an average of 90% recycled material. At the end of a building's life cycle, 100% of the steel frame can be recycled with low environmental impacts on a per square foot of construction basis. Steel is the premier choice for environmentally conscious sustainable projects. So, structural steel is green precisely because you can recycle them. So, for example, the usual lifespan of a building is 50 years. So, after 50 years, you are not sure of its serviceability anymore or strength. So, you may need to demolish them and construct a new building. So, in this particular case, if your building is made of steel, you can recycle the materials. No? So the recycling of steel is pretty much simple. You just have to melt it and then you reform it, just like that. No? But then you need to watch out for the chemical composition of steel. So although recycling can be done, it will be a bit more work. Unlike in concrete, for example, if you demolish a concrete structure, you can only recover and recycle the aggregates. The paste, the cement paste, no? You cannot recycle it anymore, so it will be left as dust. No? So it would harm the environment more than steel. Okay? Although in reinforced concrete, you can still recover and recycle the steel bars, the reinforcements. You can still recycle them. And lastly, there's always a solution in steel. No matter what specific project challenges arise, structural steel framing systems can meet them. So, structural steel allows can be used for a lot more framing systems or structural systems rather than concrete. So, for example, you cannot use reinforced concrete for bracing precisely because we know that concrete is strong in compression but weak in tension, and bracings can be may be subjected to either tension or compression. So meaning concrete is not a good choice for bracing systems. So steel can be, on the other hand, can be used because we can assume that its behavior in tension and compression are pretty much the same. So we can use them as bracing. So if you actually read the list of structural systems for earthquake, no, in I forgot what table is that in NSCP, but it is in section 208. The list of the structural systems for steel is a lot longer than that of concrete. Okay, so do you have any questions so far? Okay, none so far. Okay, so I read, no. So Monday is a holiday, as far as I know. Yeah, yeah, yeah. Uh, so meaning we might not be able to meet on Monday. So as far as I know, we cannot meet during holidays, but I'll just wait for the final announcement from TIT. But it is almost sure that we will not meet on Monday. Okay, so let me resume. So now, before we proceed with the structural steel design itself, we need to first recall what is structural design. Structural design may be defined as a mixture of art and science, combining the experienced engineer's intuitive feeling for the behavior of a structure to produce a safe, economical structure that will serve its intended purpose. So, So if we observe here, it is said that it is a mixture of art and science, now, precisely because structural design also considers the functionality and the aesthetics of the structure. Now, although we do not really double match with that aspect, it's more of architecture than structural design. Okay, we are more on the sciences, although we also consider this a bit. We consider art a bit. Combining the experienced engineer's intuitive feeling for the behavior of the structure. So that's why you take statics, you take dynamics, you take strength of materials, structural theory, and all. No? It is for you to have an idea how structures and its components behave uh, when subjected to different actions. So, for example, you expect a beam to bend. You expect tension members to either elongate or shorten because they are subjected to tension or compression. Columns may buckle or crush. No? So on and so forth. To produce a safe, economical structure that will serve its intended purpose. Now, if you observe, the word safe comes first before the word economical, precisely because we need to uh, We need to prioritize the safety of the end users before you consider the economy. So you need to balance the safety or the quality of the structure compared to its cost. Okay, so so if you attended your CPM class, there is a triangle of conflicting constraints. We need the cost, the time, and the quality. So you want a project to be done at the highest quality possible with the lowest cost and the fastest time. So you need to tweak your structure such that it can be done within those constraints. Okay. However, since we are in a structural design, our priority here would be the quality and the safety. That's why the first keyword here is safe rather than economical. Okay, that will serve its intended purpose. So that's why we have, aside from the strength requirements, we also have the serviceability requirements. That is, in order for the function of the building not to be im- uh, impeded. So for example, if the deflections are more than the code requirements, that would mean that some non-structural components may not be usable. For example, if you have doors and windows resting on a wall that is rested on a beam, if a beam deflected, that means the doors and the windows may not be open. So that's one example. So now, what do we consider in structural design? So typical criteria for evaluation of structural design are as follows. The minimum cost, well, pretty much self-explanatory. No? Minimum weight. So if you paid attention on your earthquake engineering course, the less weight the structure has, the less effect the earthquake will be. Okay, because if you remember the formula for the base shear is a function of the weight of the structure, and they are directly related. So meaning, if you have more weight, the base shear will be more. If you have less weight, the base shear will be less. Okay. Next, minimum construction time. So you want the structure to be used as soon as possible, right? Minimum labor, pretty much related to this, the minimum cost. Minimum cost of manufacture of owner's products, again, related to this. And maximum efficiency of operation to owner. Meaning, we want the owner wants to use the structure for as long as possible. No? So, the usual lifespan of a building is around 50 years, whether it's steel or concrete. In concrete, you can expect it to be a lot less, so around 35 to 40 years. In steel structures, though, you can expect for a lifespan of around 50 years. Okay, so there you go. So now, how do we actually perform structural design? So the typical design procedure for structures are composed of two parts usually. We have the functional design and the structural framework design. Functional design is designed such that it will support the intended use or function of the structure. So this one is usually taken care of by architects and the other engineers, such as electrical, plumber, master plumbers, sanitary engineers, etc. Mechanical engineers na. So it includes adequate working areas and clearances, So this one is for architects, proper ventilation and air conditioning. Mechanical engineers will be the one for this. Adequate transportation facilities. Usually, architects and civil engineers work on this one. Adequate lighting, uh, electrical, and aesthetics, architects. Okay, so we will not double match with this. Okay, the one that we are concerned with is the structural framework design, the arrangement and sizes of structural elements so that it satisfies the code requirements. No? So it carries the required loads. It will not go beyond the certain serviceability requirements and so on. Okay. Now, we will focus more on the structural framework design. So the structural framework design is usually iterative in nature. When we say iterative, it means it repeats itself until you satisfy certain criteria. So there you go, meaning the process goes on a loop until certain criteria are fulfilled. So what are the steps in performing the iterative design procedure? So we have a flow chart here. No? So I have the planning, preliminary configuration, the loads, member selection, structural analysis, evaluation, and then there's a decision part here. So based on the results of the analysis and design, do they satisfy the code requirements? If yes, it is. If yes, that would be it. If no, you need to start all over. It can be here or here or here or as far as here. So it's not always, you will not always repeat at the planning process. No? You may repeat it here. So it depends on what specific code requirements were not fulfilled during the evaluation. No? So it depends on where you will repeat. Okay, but it can go as far as the planning stage. So let me discuss each step. What do we do in each step? So first, planning. It involves defining the use and function and overall look of the structure. The owner and the design professionals are involved in this step. So all of those involved in the project are in the planning process. So we will talk about you will talk about the client specifications, the client preferences, the requirements by each of the professionals. Say for architects, it would be the clearances, the building code requirements. For the other engineers would be, for example, in electrical, would be the power load, the lighting requirements, etc. All of those. So it in planning stage you detail all of the requirements, no, by everyone. Okay, then depending on the results of the planning process, the structural engineer will now arrange the structural elements based on the specifications set during planning. So that would be the preliminary configuration. So preliminary because it may change. So depending on the results of the evaluation, I have shown this earlier. So so how do you do this? You arrange the elements. For example, I put a column here, or I put a beam here, etc. Okay, so there you go. Then next, establishment of loads. So what are the loads to be applied on the structure? So again, it is based on the client specifications, no? And the loads are based on two main factors: materials that you will use, and so because the materials have have their own self-weight. Okay? So you will consider them. And at the same time, function. So for example, if the building is for residential purposes, the code prescribes minimum design load for say residential projects. Then for other purposes, it also gives you the minimum design loads. And at the same time, you will also consider the conditions of the site. So for example, if the location is typhoon typhoon prone rather, so you will consider higher wind loads. If it is near faults, you will consider larger earthquake loads, etc. Okay. After all this, uh, you will now select you will now select your trial sections. So preliminary member selection. So based on the loads and the configuration, together with the experiences from previous projects, you may estimate what should be the size of the members. Okay. So for example, if based on the configuration and the loads, you will know that a column will carry more load than the others, then you will assume that it will require a larger section. So you will use a larger section for that one. Same thing with the beams. Same thing with the other members. Okay. So there are some methods that some experienced engineers use in preliminary member selection. So I think I will show this on the other session. Okay. Next, after you have established everything here, in the last three steps, the configuration, the loads, and the trial sections, you will now analyze the structure. So usually, we use softwares for this. uh, So, however, in the olden days, they use manual. They do this manually. So that's why if you observe in your structural theory class, you do say portal method, cantilever method, all those approximate methods. It is because during the old days, you do manual calculations. So, but then, so I have said earlier, you use softwares for this usually. However, it does not mean that if you run it using software, it is correct. You still need to check this manually. So using the methods that I have said earlier, portal method, cantilever method, whatever method it is, or you can use the exact methods like say slope deflection, moment distribution. No? The reason for this is that the software only performs the instructions depending on how the software is developed. So it will only follow instructions, but the inputs, uh, importantly, the inputs come from us, the users of the software. So if the inputs are wrong, then the results will naturally also be wrong. So that's why there is a need for you to still perform manual check for the analysis. Okay? So we always encounter the saying GIGO, which means garbage in, garbage out. If you have a garbage input, do not expect a correct output. You will also be you should expect a garbage output in that case. Okay? So once you have done this, there will be evaluation. So you will now evaluate the results of the analysis using code provision. So this is the design portion. Okay. So what are the codes that we use? So for so we use a building code. So in this case, we use PD 1096, the National Building Code of the Philippines. No? However, this is more of a domain of the architects. No? So we use more of the design specifications. So because it gives more specific guidelines for the design of structural members and connections. So in the Philippines, we use NSCP 2015 NSCP Volume 1. So this is the latest iteration of the structural code. Okay. So we use the provisions from here to check and design the structure. Now, once we have checked and the design uh, may not be adequate for some reason, no? So there is a decision part here. Do all members and connections satisfy code requirements? So if it is no, then you may be able to go. You may go back to any of the steps here. So it may be, well, maybe the trial section is too small. No? Maybe the load is too low. No? Maybe we can change the configuration, etc. Or maybe in worst case scenarios, we can change some of the specifications that we talked about during the planning process. So you can go anywhere here if you think you have not satisfied most of the all of the code requirements. No, however, if for example you have fulfilled everything here, you have satisfied everything here, then that's a time that you can say that that would be the final design. No? So now I would add something here for the redesign, for the evaluation and redesign. Uh, you do not just although the main criteria that we use here are the code provisions, it's not the sole criteria for the for deciding whether the design is final or not. You will also consider other factors like cost, construction methodology, and all. No? So code requirements are the main criteria, but it's not the only criteria that we need to consider. You will also consider the other criteria here. Okay? So that. So that is the iterative design procedure for structures. So do you have any questions so far? All right. So no questions so far. So let me proceed with the next part. So next we will be having the loads. We will only cover this quickly because paulit-ulit eh. You already discussed this during your structural theory class, your earthquake engineering class, your other design courses like reinforced concrete. No? So we will only go through this a bit more quickly than usual. Okay. So as we remember, the third step of the iterative design procedure is the establishment of loads. So loads to be applied on structures depend on its function or use, material, and other considerations such as actual site conditions. So now, how do we determine the minimum loads that we need to consider? So minimum design loads for buildings are listed in Chapter 2 of the 2015 NSCP. So you will be able to see that here. Okay. So different types of loads that are usually considered in structural design are as follows. So we have the gravity loads, we have the environmental or calamity loads, and the other loads. So go through this one by one. No? So first, these are the forces that act on a gravity loads are forces that act on a structure which is due to gravity. Okay. So gravity loads are also called vertical loads precisely because gravity is always going vertically downward. Okay. So what are the sub-classifications of gravity loads? We have the dead loads, live loads, and vehicle loads. So for dead loads, these are permanent gravity loads. So it will not change its location or magnitude. Okay. So we can say that dead loads are static in nature. So the minimum dead loads can be are listed in section 204. For live loads, these are loads that gravity loads that may vary on time, location, and other factors. So this one may either be static, dynamic, or cyclic in nature. When we say dynamic, it changes in magnitude over time. Cyclic, it uh, it goes through uh, a repeating pattern. So at times it is there, at other times it's not there. No? So it's periodic. So minimum live loads are in section 205. Next vehicle loads are due to vehicular weight and motion. So they are either static or dynamic in nature. So vehicle loads, they are not really in a CP, but you can find it in other codes like the DPWH standards. Now, since we mainly use vehicle loads for bridges, although we also consider vehicle loads
Parking.
in parking buildings. No? So it's the domain of NSCP Volume 1. Okay? So that would be all for the gravity loads. Next, we have the environmental or calamity loads. These are loads that act on a structure due to environmental process. So these are called calamity loads also because these environmental processes affect the structures usually while natural calamities are happening. So in normal situations, they do not really pose much effect on the structure. So what are the two environmental loads that we usually consider? First, we have the wind loads. So due to wind action and structure. So these are actually dynamic in nature since the wind may change in speed or pressure. But as a simplification, we have equivalent static loads. Okay? So we convert the actual dynamic wind loads to static wind loads. Although it does not actually reflect the actual behavior, it does not actually give us the actual behavior of structure due to wind. It only estimates. Okay. So minimum wind loads are listed in section 207. So there you go with wind. So here is a video about the to know more about the effects of wind in the structure. So let me see how long is this one. Okay. So around 10 minutes. So I don't think I can load this one. So you may watch this on your own. Okay. So next we have earthquake loads. So these are due to earthquake or severe ground motion. So again, earthquake loads are actually dynamic in nature, but equivalent static loads are can be used. But then, how again, having equivalent static loads does not mean that we reflect the actual behavior of structures. No? So, no, earthquake loads to, sorry. Okay. So minimum earthquake loads are listed in section 208. Okay. And again, I provided a video no, about the behavior of structures due to earthquakes. So how long is this? 5 minutes. So again, I think you can watch this on your own. Okay. So so these are the two main environmental loads that we consider. Okay. So for the other loads, so there are other loads that we may need to consider. No? So like soil loads due to either lateral or vertical earth pressures. No? So this one, you will discuss it in your foundation engineering course. So I will not discuss this further. So pretty much like for fluids, soil may also exert pressure on structures, especially if, say, if you have basement. No, you will consider the effect of soil on the basement walls. So that would be it. Flood or rain loads due to severe flooding or high amount of rainfall. Okay. Fluid loads due to static and or dynamic fluid action. So especially if you design water tanks, you have to consider this. Impact loads due to dynamic loads exerted by the other components of the structure. So for example, if you have elevators, there are impact loads. Or say in factories you have cranes, you also need to consider the impact loads contributed by the lifting action of the crane. Okay? Then blast loads due to high pressure loads applied within a very short time duration. So for example, if you want to design a military camp, you don't want your camp to be bombed easily. No? So that's why you need to design your military camps considering blast loads as well. Okay? So here for it discusses how some loads may affect the behavior of the structure. So let me just play this. Uh, it's 7 minutes now, but not all. So not all of this you will watch. So I'll just skip this one again. So watch this on your own. Okay. So do you have any questions so far? All right. So there's still no questions so far. So I also have some additional videos. You can click this one. No? However, you need to go through the other parts of the module first before you access this one. Okay. So we are now in topic 1.3. You need to go through topics 1.4 to 1.9 before you will be able to access 1.10. Okay. So let me proceed with this one. So now we know how to evaluate loads. How do we go around with the structural design process? So now, what exactly do we need first to do in order to design using structural steel? So the main underlying concept behind structural design is that the capacity of a structural member to resist given loads should always be enough to address the demand due to these loads. So that's the main concept. So the capacity is greater than or equal to the demand. Okay. So at, at the moment that the demand exceeds the capacity, meaning the structural member may fail. Okay. So structural design involves consideration of limit states of the structure. So what are limit states? Limit states are the conditions of a structure at which it ceases to fulfill its intended function. So by the time, for example, even though if it is not collapse, if it does not fulfill its intended function anymore, then meaning the structure has reached its limit states. Okay, so generally there are three types of limit states as follows. We have the strength limit states, serviceability, and special limit states. So strength limit states, these are limit states that depend on the capacity of the member. So what are the examples of the strength limit states? Say buckling, fatigue, or fracture. So this failure modes uh, happen due to the demand exceeding the capacity. So that's what we call strength limit state. Another type is serviceability limit state. So these are limit states that mainly affect the use or function of the structure. It does not necessarily exceed the capacity of the structure, no? but it can impede the use of the structure. So what are the examples of this? Say excessive deflections. So excessive deflections may lead to some features of the structures uh, to uh, to be unusable. So for example, if a beam above a door deflected excessively, you may not be able to open the door normally anymore. Okay? Because the door will be compressed. Another thing is we have excessive vibrations. If you observe, if for example, if you walk and then you always feel some vibrations, you feel some discomfort. So in turn, you will not be confident in using the structure anymore. No? So that's another serviceability limit state. Okay? And then lastly, we have the special limit states. These are other limit states that may be deemed necessary to consider. So other limit states apart from this two, we list it as special limit states. So these are usually added for consideration during the planning stage of the design process. So meaning we decide some of these special limit states depending on the client specifications and preferences. So we will not double more on this. So usually we will focus ourselves in design considering these two types of limit states. So now, what are the design philosophies that we use in structural steel design? So the AISC propose two design philosophies. Actually, there are three, but we mainly use two. Okay, so I will change this later. It is three. So, what are these three design philosophies? We have the allowable stress design, we have the load and resistance factor design, and we have the plastic design. So, ASD, allowable stress design, in reinforced concrete, we call it the working stress design, okay, or the elastic design. So this is the capacity demand expression for the allowed ASD. So this Rn over omega is the capacity of the structural member in ASD. So Ra is the demand due to load. Okay. So now Rn over omega. Rn is the nominal capacity of a structural member, assuming ideal conditions. So what does it mean? For example, if you have a structural member, it has a material and section properties, you may be able to evaluate the capacity of that particular structural member. So for example, in terms of in flexure, you will determine its moment capacity. if axial tension or compression, you will be able to determine its axial capacity. Same thing with shear and all. No? So this one, we usually give it using the code specifications. No? So depending on the type, on the action that you consider, this may be different. Okay, so this will be different in tension, in compression, in flexure, etc. Okay. Then, what about this omega? What is this for? Omega is what we call the factor of safety. Now, why do we put a factor of safety? So, this factor of safety is always greater than 1. Okay? So, why is it that we divide the nominal capacity by the factor of safety? If we remember, this nominal capacity depends on ideal conditions. So, ibig sabihin, the material property is consistent, the section property is consistent, the workmanship of the structural member is perfect, no initial damage, no imperfections. No. However, in reality, it doesn't go that way. No. So, what do we consider when we put a factor of safety? We consider three: material under strength. So, meaning, for example, we assume the yield strength of a steel to be around, say, 40 KSI. The actual may be less than that. Maybe, okay? Or maybe greater than that. Workmanship. So, for example, if there are construction issues, then you may not be able to attain the condition that you want. Okay? And overloads. The loads that we enumerated earlier on are just estimates based on the some studies. No? So meaning it does not always we cannot always say that the loads will be always like that. It may even be greater in some cases. So for example, if you have a residential building and then suddenly you have more visitors, meaning the load will be a lot more than the usual. So we also need to consider those situations. That's why we put a factor of safety. So it is just like that. Okay. So now let us go with the second philosophy, the one that we will, that one that is more normally used in structural design. We have the load and resistance factor design or LRFD. So in reinforced concrete design in RCD, this one is called the ultimate strength design, no? Or more normally, we also call this the limit states design. So the demand capacity expression would be this one. So this one is the capacity and this one is the demand due to loads. So again, Rn is the nominal capacity. Then we have phi. This phi right here is called the strength reduction factor. And this strength reduction factor is used to consider material under strength and workmanship. Uh, Now, how do we consider the overloads in that case? So the main difference between ASD and LRFD is that we consider the overloads differently from the material under strength and workmanship. Okay? So this RU and RA are pretty much different. So I will explain more of this later on. Okay? So RA is used in allowable stress design. This one, the RA are just service loads. So meaning you just add up the loads as it is. However, in LRFD, we use RU. No? This is the total demand on the structural member due to applied loads amplified with load factors. So these load factors are the ones that we use to consider overloads. Okay? So that's why we put this statement RU is summation of gamma I Ri. So this gamma I Ri is just the load multiplied by a certain load factor, usually at least one. Okay? So load factors are used to consider overloads and uncertainties on material weights because, for example, if we say that the density of steel is 7750 kilogram per cubic meter, no, that's just an estimate. The actual density may be different from that. Okay, so we also consider those uncertainties, and the load factors depend on the type of load considered. Okay, so if you have already taken RCD, we have this particular load combination 1.2 DL plus 1.6 LL. So the dead load there, the load factor is 1.2. The live load, the load factor is 1.6. So now, for each type of load, we usually consider different load factors. The main concept there is that the higher the uncertainty of those loads, the higher the load factors that you need to use. So in dead loads, it is just mainly depend on the self weight of the structure. So meaning it only depends on the material weights. And material weights, although we have the estimates and although they may be different, it will not differ by much. There will not be much difference. So that's why the load factor there is lower, 1.2, for example. For live loads, though, it, it has a higher degree of uncertainty. So live loads may be a lot more or maybe a lot less than what is in the code. That's why we use the load factor 1.6 in live loads because of the degree of uncertainty. Okay, so that's the reason behind the load factors. Now this VRN right here is the ultimate capacity or design capacity of the structural member. In ASD, that design capacity is this one, the Rn over omega. Okay. So another note here. So do you have any questions? So well, there's one. Saan po makikita screen recording ng discussion today? I think it will be saved on the concluded conferences dun sa group conferences nandun. Okay? So you can just wait for this conference to end and then I think nandun na yan after. No? So let me resume with this one. So another factor with this fee is that strength reduction factor may be different depending on what action do we consider. So for example, in flexure we use zero point 0.9. In shear we use 0.75 in RCD, right? In flexure you use either from 0.65 to zero point 0.9, but if you want tension control you usually use zero point 0.9, right? So why is it that for each action the strength reduction factor is different? It is due to the prioritization of the effect that you don't want to happen. So for example, in reinforced concrete beams, shear is much more dangerous. Shear failure is much more dangerous to happen than flexural failure, right? That's why we assign lesser strength reduction factor for shear rather than for flexure. because we consider more uncertainty, and we consider the behavior of the of that structural member if we subject it to that kind of action. Okay, so during the course of the this study, we will be enumerating the strength reduction factor for each action that we consider. Okay, so that's the main difference between the two, the ASD and LRFD. LRFD has a better basis uh, of how we determine the uncertainties, like the material under strength and workmanship and the overloads. While in ASD, the factor of safety, it is pretty much a single factor. No? Kumbaga, parang lump sum na to. Isahan na lang. Okay? And these safety factors are usually due to derived due to the previous experiences. That's why this one is a bit less reliable than LRFD. So we take note here, LRFD is the more accepted design philosophy due to rationality of the factors used. So the reasons behind these factors that we use. Uh, and then another note here, if we multiply this, the omega, the factor of safety, by the strength reduction factor, for gravity load combinations with live load equal to 3 times the dead load, if we multiply them, the result will always be equal to 1.5. So they made it this way, no? Para maging much more consistent. Now, if you have, now you may ask, which one of these philosophies may may give a larger section? For example, you design a beam using ASD and you design the same beam using LRFD. Which would you expect, which of the philosophies would you expect to give a larger section? So the answer would be ASD. You may you may think, sir, we have load factors here. So why is it that ASD still gives the larger section? It's because also of the assumption on the material behavior of the steel. ASD only allows, only constrains the structural members to behave in the elastic range only. So we will talk more about the stress strain relationship of steel that's meeting. Okay? While in LRFD, it considers not just the elastic range but also the plastic range. Okay, so I will talk more about that next meeting. Okay, and then the last design philosophy here would be the plastic design, although we usually perform this only on beams and frames, no? So plastic design is used for considering collapse or excessive deformations caused by highly amplified service loads. So more details on plastic design will be discussed in module 4. So this one, we do not use them on other structural members. So in this course, we will focus more on this first two, the ASD and the LRFD philosophies. And then, depending on the design philosophy used, appropriate load combinations must be used in determining the critical magnitude of the load to be used in design. So we use load combinations. No? For ASD, we use service load combinations. No? So without the load factors, no? Because it is already considered in factor of safety. While for LRFD, we use the factored load combinations. So, so here we have the load factors. No? So that famous 1.2 DL plus 1.6 DL, it is here. Okay, so the specific sections are in 2.3.3.4 for the service loads and 2.3.3.2 for the factored load. So any questions here in this? Okay, how can we access that module? What module is this? If you pertain to 1.10, well, you can just use Canvas. You can read it ahead in order to access the new topic 1.10. No? So, ganun palagi pag sa Canvas. No? We just read everything in order. No? And then after that, you will be able to access everything else. Okay? Any more questions? Yung makikita recording, pinanggit ko na to kanina. Nasa ano, pag kinongclude ko na, pag tinapos ko na yung conference, that's the time na makikita mo na yung recording. Doon rin sa kung saan mo kinlik tong conference na to. Nandun rin. Okay. Other questions? Module 1 on my account module. It should not be. Module 1 is already it is unlocked way earlier in last Monday. It is already unlocked. So or maybe you just have not accessed the you have not read about the course module yet. So you need to read in order. So you start with the very first module, which is the about the course. After you finish that, then that's the time that you will access module 1. Okay. So any more questions regarding the discussion? I don't think there are any more questions. No? So let's see what we still don't have. Okay, so it's already part 2. So okay, I will discuss this part 2 on Friday. So there will be meeting on Friday again. Okay, same time 7:30 to 10:30. So but before we proceed before we end this one, so let's just view the other videos that we have. Okay. So in 1.10 downloadable materials. So here the videos about the loads and actions. No, so let's just play this one by one. I just want to waste a bit more time. Again, so may question. Sir, nasa Canvas din po ba makikita parameters ng project? I think I've already uploaded it on the you can check the announcement. May Google link ako doon about the design project. Okay? So hanapin nyo na lang yung announcement doon. I think I have posted it yesterday evening. Also sa Facebook group, nandun rin. Meron ding Google Drive link doon. So nandun. Okay? So, okay. So let me just play this one by one. So first, where do loads come from? So gravity loads, and lateral loads. So those are the two main classification of loads. So you can still access it on the module. Nandiyan lang naman yan. So I'm just playing this one. Types of loads. We have axial tension. So these are the actions that we consider in design. So there you go. So axial tension, axial compression, bending, shear, and torsion. Okay, so how do we evaluate? So how do loads go from member to member up to the foundation? So this one. So that's how the gravity load is distributed. It goes through the slab and go through the beams and then go to the columns. And then lastly go to the foundation and then we transmit it into soil. So that's how we distribute the loads. Then for the distribution in beams, so they only consider here one way slabs. No? So that's how we distribute the loads. And next, for girders, it's pretty much the same. No? And then for columns, that's how it goes. No? And then how about for the lateral loads for wind or earthquake loads? For example, if you have already evaluated the loads, so you will distribute it. So you divide the load among the floors. So usually in brace systems, you let the braces carry the lateral loads. No? So that's the process on how you transmit, how the lateral loads are transmitted, no? From brace to brace until you reach the foundations. Okay. And then the reason why we use lateral bracing, so the reason is very simple. If you don't want, if you want to design a building without bracing, you just need to make your members larger. However, that would be uneconomical. So it would be much wiser to provide bracing. Okay. Okay. So again, another question, sir. Kailan po na malalaman yung assigned structure per group para di po mapag-meeting, para din po mapag-meeting members ng group? I think I can give it either later or tomorrow. Okay? So you just wait for the additional announcements. Okay? So other questions? Okay. Pwede po ba kami gumawa ng sariling group ever? Actually, makakapag-form pa kayo. Okay? So, pwede pa kayong bumuo ng groups. Okay? So, based on my list, may 6 pa na wala pang group. So,